So this one is lecture number 14, and here we will talk about further methods of estimation. So coming to outline of today's lecture, first I would like to discuss about least square estimation. That means we are having a proper error function, and we try to define what we call it a square error, and after that we try to minimize, try to find minimum value of that. That means least value of that error. So that error would be given by the difference between the response variable and whatever hypothesis we are assuming. Whatever hypothesis we call it xi, for each I here meant for sample. Sample number, sample 1, sample 2, and we parameterize the hypothesis function with some parameter theta. We parameterize that, and there is a difference. That difference we are calling it error. Here this would be error, and we will minimize a square of error, because uh, it is a square of error is what it is talking about. Very nice function. What kind of function it is? Quality function. So you can easily do optimization of this one, or estimation of with this square function. That's why we are taking a square function. If you take just this error function, then you will face various issue, and some cancellation would be there. So there would be issue if you directly proceed with this error. So we always proceed with a square term. And then after this I will talk about maximum likelihood estimation. What is happening that here we come up with some kind of, we assume that data is coming from some kind of distribution, and we put a condition that source distribution might be of some kind of might come from some class of the distribution function, and that class of distribution function we try to parameterize by again theta, and we try to, after that we define a likelihood function, and we will maximize that likelihood function with respect to theta, and in that process we will get an estimate of theta. That would be our uh, uh, estimated value of the corresponding parameter. One estimate of theta we will get it through this approach. So coming to first approach, that least square estimation. So what does we do? So in last class I had already mentioned that suppose we are having one regressor, one response y. That means y you want to estimate, and y it happens to be it depends upon some function of x1, x2, x3, x4. All these are attribute. You can say that n number of observation. You can simply say that, and y depends upon this one. But through which function it is depend, we don't know. We don't know. This one is unknown. So here we will apply parameterization. The relation between y and xi is that xi, these are just actually p. I have taken p number of attribute. So p number of attribute or p number of features, attributes or input, all these are same. You can say that. And during very first module I had already described that feature variable, input variable, all those are common names. So you can proceed with any of those names. So the association we want to get here, this f is unknown to us. Then how we can estimate this f? So here I will talk about parametric approach, that we need to parameterize this f, and after that we will get an estimate of this. So if you estimate, then whenever we say estimate, suppose that estimate is happens to be f cap, or you can say that f xi parameterization by theta, then definitely there is error. So if you take difference from yi, there would be error. That error we denote it by epsilon I. So there is error, and we will estimate the parameter theta by minimizing the square of error, sum of a square of error for each sample. There would be m number of samples. So for each sample we will define error, and we will do a square. After that we will sum all those a square of error, and after we will minimize in order to get one estimate of theta. So functional form generally we parameterize by theta, I told, and hence we are getting this form. That means for ith sample, this is the hypothesis function, or this is the, you can say that this is the approximate function parameterized with theta, and definitely it is not giving exact value of yi. It is not equal to exact value of yi for each xi. There is error. That error term is epsilon I. Okay. So the typical assumption I had already mentioned, that we used to put that whether you, what kind of hypothesis function you want to take, whether you want to take linear or non-linear, depends upon your situation. But it would be always linear, which is if you are go for in this course you will always go for linear in theta. And here this x, this data matrix, it may contains non-linear structure, non-linear basis function, non-linear feature function. So those things you know that we had already discussed enough regarding those things. So coming to estimation. So in estimation process, actually estimation is an optimization problem. So here we are having error term with respect to each sample, and we do a squaring and summing all those error term with respect to all the samples. That means we are having m number of samples, then we are getting this term. This term you can call it sum of a square of error, sum of a square of error. In short, we can call it sum of a square of SSE. So as short name I am calling it SSE, and further you can simply give, from function perspective you can give name S. And here remember that the response variable y and the feature variable x, all these are what data, it is forming data set. And we are taking how many sample size, varies from 1 to m number of sample we have taken. So in this you can say that it is a data set. So data set is in when you are defining your objective function. That means in order to optimize the parameter, then this data set is just an argument. It is not a variable in sense, it is coming directly from, it is fixed kind of thing. So that means we are, once we are taking a sample, it is fixed kind of things, it is one kind of argument. But theta is variable, we have to optimize this function with respect to theta. Okay. And here how we can optimize. So we are trying to find minimum. This one is just error kind of function, and generally if this function happens to be convex in nature, this kind of a structure, so we are going to minimize this function with respect to theta. Then how we can minimize? Then you know from calculus, and we have taken here a square kind of function. So a square function is always what, a very nice a smooth function, and you can talk about differentiability of that function. That's why we had taken a square function. So in order to minimize this function what we do, our target is need to minimize with respect to theta. So we have to differentiate this function s, some of square error, with respect to theta. After differentiation we are getting this, and what we do, we have to find a critical point. What is critical point? Anyone can say that? I think critical point is very much common. What is meaning of critical point? Anyone? For a function, what is critical point? No, critical point. What is zero? Differentiation. Suppose function is not differentiable at a certain point. Then how can you say that that point would be critical? Any? But I haven't mentioned that increasing, decreasing. Till now, increasing, decreasing, you can investigate through inequality or through the sign of derivative. From there, you can say that. But simply, a definition of critical point is that where your derivative vanishes. Other, if derivative exists, where your derivative vanishes, that is zero. And other, where derivative is not existing, we can't able to differentiate, that will be also candidate of a critical point. If some point like mod x, if you take function mod x is not differentiable at zero, definitely zero, then we can take that zero as a critical point for mod x, function mod x. So if the differentiability fails, then the point where differentiability fails also you can consider as a critical point. Apart from that, what other, like if you take boundary point, so generally in boundary point we used to define one side derivative, so it is not possible to define both side derivatives, so those boundary point also we consider as critical point. So boundary point, uh, first simplest one is if function is differentiable, very nice, just find the derivative equal to 0, that would be your critical points. Okay, there is no issue. But apart from that, if you are having those points where you are facing that function is not differentiable, it is not differentiable, the due to that non differentiability of the function, those big points becomes critical point as well. So those are so this is meaning of a critical point. This way you can find it out for every function. So we'll go forward. So here just you have to find the critical point, but this one is a square function, so very nice, it is a differentiable function, very much a smooth function. So you can find derivative of this function s with respect to theta, and derivative is coming like this way. It is very nice derivative form it is taking. So you have to equate it to 0. After equating to 0, then what thing you will get, you will get a system of linear equations. That system of linear equation, it is not giving exact solution of the this problem, exact solution of this problem it is not giving, but when you solve this, it will give a solution that would be an approximate solution, theta cap. So that's why we are saying that another few people are calling solution of this one least square approximation. Least square in linear algebra, I had discussed a solution of this normal linear system as a least square approximation. So it is giving a solution. This solution is not exact solution of this one. I am again saying it is an approximate solution. That's why this is providing solution of this linear normal linear equation is an estimator, and it is giving an estimator. Solution of this one is estimator, that we denote it by uh, uh, theta cap ls. Ls meant for least square. The method what we have applied here, least square, because objective function we are defining in term of a square and we are finding least value, that's why least square. And this estimator, we are calling it least square estimator of theta. Least square estimator of theta. So name and everything is hidden here, why I am calling it, everything is revealed, why we are calling ls estimator and other things. Okay, so definitely it will give one estimate of theta, and it would be also a function of your data. If you change data, then you will get another estimator. So that's why it is a function of this data set. Whatever data set you are taking, this value l theta cap ls theta cap ls, it will be influenced by given data set, whatever data set you are taking. And I think it might be clear to everyone here. Theta cap we are getting as a solution of normal equation, not as a minimum of this problem. We are not getting as a minimum of this problem, we are getting as a solution of this normal linear system. So we are solving normal linear system in order to get theta. Suppose we assume we are giving that hypothesis function a simple form, that this linear form. That means suppose the hypothesis function is a linear function of theta, and x is coming from some basis feature maps, depends upon what choice you want to take. Then using linear algebra, the objective function becomes uh, as a sum of residual, like this way, sum of residual like this way. This one is the compact representation in vector form, why it is coming. So we had, for a single sample we had taken like this way, uh, it would be, you call it some basis represent, call it uh, basis function representation xi transpose theta. This one is for first sample, likewise you will go for nth sample. transpose, and if you take this as row, then you will get a representation response vector coordinate of y are y1 y2 y3 to ym, and here this will take data matrix form, and here theta will come. So here you can assume that this we are taking as a hypothesis function, and with respect to that, this sum of square error is taking a very compact representation. Here all m number of samples are coming together, and they are forming a matrix vector representation of the same problem, this linear system simply we can call it. So from there we are getting a compact representation like this one, y minus x theta. It would, y is what, m dimensional vector, x is data matrix, theta is the parameter that p dimensional, whatever dimension you want to proceed with the features. Okay, and same thing is just a dot product. If you sum it up, expand it, you will get this one, you will get this one. So, first optimality condition, first order optimality condition say that find the derivative of this error function with respect to theta, sum of square error function with respect to theta, and equate to 0. That means if you differentiate it with respect to theta, then simply this in the vector form you will get this term. Here why I am taking here, you will see one explicit representation of normal equation. That's why I am coming with. Just now, after that, solve this equation. After solving, you will get a form of like this way. If you solve this, you will get a form like this way. What you do, expand it, so you will get here y minus you know that you can reverse the order as well. So if you open the transpose, what would be this? It would be like this way. And what you do better, you take transpose with this side. It is a better representation. So do transpose both side, and you will get this representation. X transpose, order is changing. If you with respect to transpose, I am taking transpose both side in this normal equation, then order will change. X transpose will come first, X transpose of this will come, and this, what does it become? Transpose of transpose is it is a dual operator. Transpose is a dual operator, so transpose of any transpose is again the same quantity. So it would be y minus x theta x. This is bold x, that means it is a data matrix equal to 0. Further, if you simplify, then you will get x, this bold x matrix, data matrix transpose y minus x transpose x bold x theta equal to 0. So what you do here, theta is unknown to you, y is given, x is also given, and then what would be theta? Suppose this x transpose x, it is invertible. When it would be invertible? When x happens to be a full rank matrix, then x transpose x would be invertible. Why? Because it would be always a symmetric matrix. Also, it is a square matrix because of this x transpose x. Okay, so we can get so directly I'm writing it here. I should write it theta hat, because this one is coming with respect to normal equation. It is not directly dealing with this linear system, it is dealing with normal system. So theta hat, we will get it like this way, x transpose x inverse, because we are putting a condition over data matrix that one is full rank matrix, that's why it would be invertible. Otherwise, if it is not invertible, there is no issue. You can find a pseudo inverse with respect to SVD. I had already discussed about pseudo inverse, so you can find, so with the help of SVD you can define pseudo inverse as well if this data matrix is not invertible. So anyhow, you are getting an approximate solution, this theta cap. So it is one estimator of theta, and it is explicit here. X is known to you, y is known to you. So in right hand side, everything is known to you. That means you are getting a numerical value of this one. from the data set you are getting if you are having information about data set, then you are getting a numerical value of numerically this your estimator you are getting. That's where this estimator, how you got it? So you got it through least square estimation. You got it through. So this estimator we are calling it least square estimator, and it is generally with respect to linear function of the, it is a linear function of the data, whatever data you are proceeding with. So moreover, if you try to see this least square estimator, then what is happening that you can further take a standard form of this one. You can relate it with the actual value of theta. How you can relate? So here through this, by solving this normal equation analytically, so we are getting this solution now. But y is what? Y we have already seen that we are taking hypothesis function, linear function. So that means data matrix time, our parameter theta, unknown parameter theta. So we will substitute this y in place of y. We will write this term linear function, and after that we are simplifying. Plus error term is also coming. So so we are simplifying. So what will happen? So here x is what? X will come with this one x transpose, and both what it becomes inverse of x transpose x and x transpose x. So what is the product of these two? It because the product, this one is inverse of this x transpose x, so that would be anti-matrix, and anti-matrix times theta is giving theta. This is the true parameter times, and epsilon is coming with respect to error, this linear model. So here epsilon, this error term is coming. So this error term you can call it residual error. This is the residual error, you can call it like this. Okay, residual error. And you can remember that if I'm calling it in this least square estimation, what is the estimation error? So estimation error is just the difference between the estimator theta hat and theta, and that is given by this inverse of x transpose x minus x transpose this error. This is your estimation error. So because why definitely this is non-zero. So always if it is an estimator, then if sample size is not exactly equal to the population size, definitely this would be non-zero. This would be non-zero quantity. And next we have to calculate the variance. So what would be variance? Variance also it can be given in the similar fashion what I had calculated estimation error. You can calculate variance of this one. And mean just what if you try to calculate mean of this one, then how you calculate mean? Then through expectation, apply the expectation operator over theta cap theta hat ls least square estimation. So what will it becomes what is this one true parameter? So expectation of theta is what? It would be theta equal to theta because it is a single number. It is a value of true parameter. So it would be expectation of theta would be directly equal to theta. And now if you try to calculate expectation of this term, second term, then this one is constant. It is directly coming. You have once you have fixed the data, then this would be a constant. So it will come out of the estimation. Only we will find the estimation of error. So generally, whatever model you do, linear model, generally we use to put that the error term or error, whatever error happens in that data, in noisy data, always we consider assumption that distributes symmetrically around origin. That means mean of that error happens to be 0. So that's why mean of this would, if you find expectation of this one, this would be 0, and hence we can say that expectation of this least square estimator is equal to theta. And hence what estimator you got through this approach, least square estimation, that one is an unbiased estimator. It is an unbiased estimator. Now for the same estimator you can find the variance. So variance would come like this way. This is the variance of the least square estimator. So always whatever estimator you will get, always find two things. One is expectation or mean, and another one is variance. So then you will check efficiency, sufficiency, consistency, other things you can check it. Okay, so always try to find all these. Now we will go for second part of this lecture, that here I will talk about maximum likelihood estimation approach, and also I will take few example as well. Okay, so assume a particular distribution with unknown parameter, that there is a distribution, some kind of, either it might be binomial, normal, or whatever, we don't know, but it might be any kind of distribution, and for that we don't know the parameter. So maximum likelihood estimation chooses to set chooses this set of parameter that maximize the likelihood of drawing a particular sample from that distribution. So it is maximizing the likelihood of that data is coming from a particular distribution. So consider a sample of size n with n observations. If you are saying consider a sample of size n, that means you are performing n observation, x1 x2 up to xn, which is drawn from some pdf. That pdf we don't know, so simply I can say that that uh, distribution will have pdf or probability mass function. If it is discrete in nature, then probability mass function f of x, but we don't know. So in order to estimate this one, we parameterize as f of x given theta. With theta we try to parameterize, where theta is the parameter of the distribution. If the xi's are independent with this parameterized pdf, then the joint probability of the whole sample would be what? Just we have to multiply. So uh, f of x1, it would be density or probability for, if it is discrete in nature, then probability for first observation, f of x1 given x2 would be probability over second observation. Likewise, you are having how many? N observation, so you will do calculation of density of nth observation, f of x given theta. You parameterize through theta, and if you are trying to find uh, joint probability of all this sample, all these observation in this sample, then what you have to do? Just do multiplication. Here multiplication, we are doing multiplication. Why? Because here we have taken condition that x first observation is independent of second, second is independent of third. Likewise, independent, say id nature we have put it over this sample. Okay, so that's way you can do product. So this one is this function, whatever we are getting it here, it is your here theta is unknown to us, we don't know. So this function we are calling it likelihood function. So the function, and that's why we are giving notation L x given theta. So the function L x given theta, here x is given to you and theta is unknown to you. So this function we are calling it likelihood function. This function can be maximized with respect to theta to produce a maximum likelihood estimator, that we are calling it theta cap MLE. M meant for maximum, L meant for likelihood, and E meant for estimate. So this is, so it is we are getting this estimate. It is different approach from previous one, least square approximation. So how we can get this? I will talk. So I will take example. So it is often convenient to work with so here I have defined already likelihood function L x given theta. Here x is given to you, x is a particular data set, particular outcome. Simply you can say that particular outcome or particular data set, or whatever you want to name it, the particular outcome of a distribution. So distribution have several outcomes. So among that, x is one particular outcome that is known to us, we know about that. So we try to infer what would be that distribution. So that's why we are defining a likelihood function. This is the likelihood function. So likelihood function is dealing with product. It is defined product, because it is, if you go individual observation, then this one is defined as a product of f of xi given theta with respect to individual observation. So if product, it is not always, when you do apply calculus or do apply some kind of differentiation, integration, and when you are having product kind of function, it is not always good to proceed with. So what, so logarithmic is providing a interesting approach, that if you take logarithmic both side ln, that is log this likelihood with this likelihood function, then this product will be converted into summation. So always logarithmic function convert into summation, and if you are having a summation term, it is very separable in nature. So easily you can do calculus. Whatever calculus you want to do, you can proceed with that sum function. So that's way, in place of proceeding with likelihood function, we can proceed with the log of the likelihood function. That is, we are defining ln of L x given theta, we are defining. So due to that, we are getting a summation kind of approach. This separable structure of this log likelihood, we are getting it here. Okay, so we will find the maximum value for this one. So here, if you are applying applying log over a function, then due to log, that optimum value is not going to change. Log is not going to change the optimal value. So that's why, that due to that, if you are finding the optimal value of this function, log likelihood function, then it would be, that would be also an optimum value of the likelihood function. So log is not going to affect the optimum value. So the ML estimation approach is very general. Now, if the model is not correctly specified, then estimate would be very sensitive to misspecification. If you are not coming with proper model structure, then definitely your estimate would be very bad. So consider one example. Consider we are having a data set with 5 we are having a data set here, like this way, of sample size, or simply we can say that we are having a sample of size 5. It is a sample of size 5 values are there, 1 2 3 4, oh sorry, 6 we have taken 6 value. Okay, so and suppose these data are coming from normal distribution with mean mu and variance is 1. That means here, for this distribution, mu is unknown to us, we don't know mu, but variance we know, variance is 1. Variance is known to us, mean is not unknown to us. So we have to, with given this sample, we have to estimate this. How we can estimate? Any idea? Can we estimate this mean with this given data? Anyone can say that? How we can estimate? Not. Okay, we will see it. It is very simple. Just define sample mean. Are you able to listen me? Anyone respond? Are you able to? Whether am I audible or not? Yeah. So I told that I am saying that you are having a data set, and here assumption is that this data set is coming from some normal distribution whose mean unknown to us. We don't know the mean. So tell me one estimate of that mean. How you can get that estimate? So I told that just take sample mean of this data set, that will give one estimate of this mu. Sample mean, define a sample mean, and through that you will get one estimate of mu. It might be if your really your data had come from normal, then definitely this estimation would be fine. But suppose these data are coming from some other distribution, but you are assuming that these are coming from normal, then in that case your estimation would be very bad. So that's why this line I had written that. So proper model structure is very much essential. Right now, just assume that these data are coming from this normal distribution. Okay, so the probability of each of these point based on unknown mean mu can be written as, what is the probability of seeing 5? What is the probability? That probability we can get it from the normal distribution. We know the formula, that PDF of normal distribution. What is that? 1 by a square root of 2 pi times exponential minus x minus mu all square, uh, divided by twice of sigma square. This is the PDF of normal distribution, that we know that. So suppose the data are coming from normal distribution, and hence the data have to satisfy this condition. So for x equal to 5, you will get this is the distribution for this is the probability for each value of, if you put each value of x, that one is talking about probability. If you multiply with a small delta, with delta it will talk about probability per unit area. Or simply density is talking about what is the density. Density is actually probability per unit area. And simply similarly you can get density per unit area for x equal to 10, that multiply with delta and you are getting the density per probability per unit length, that means density. Simply you are getting value of density for x, x equal to 10. This is the density. So what would be the joint density? So do product of all these. Here x is fixed, here x is fixed, so simply we can't say that it is depending of distribution. It is not a distribution, it is just a simple fixed probability for one data. But our we don't know what is the mean. Mean is unknown to us, so that's why we try to estimate with theta, and x is fixed. So we will define a joint probability by multiplying the individual density of we will define joint density by multiplying the individual density of the points, those 5 6 7 up to 10. Okay, and after multiplication it every time involve exponential, and exponential is, if you multiply then they follow additive rule. So that's why addition of the argument is coming like this way here. Addition of argument, you can see it here. Okay, so this is the likelihood function. It is coming at like likelihood function, but you are here, you can't claim that this one is a density of the corresponding distribution, joint distribution. We can't say that it is the density of joint distribution of n number of observation or that sample. We simply can't say. Why? Because theta is unknown to us. We don't know. If till now if theta is unknown, we can't claim that theta what is, how, we can't say simply. So we need to estimate it. So the value of theta, simply theta, that maximize the likelihood, this likelihood function, this is the likelihood function of the sample, can be defined by can be calculated by maximizing the likelihood function with respect to theta. We have to maximize, and this one is very nice function. It is a smooth function, or even the argument, it is exponential with quadratic argument. So it is nice in sense that we can differentiate it easily because a square term is coming here. So I had already mentioned that in place of likelihood function, what you do, you can proceed with log likelihood. Log likelihood, what will happen? Log likelihood convert product into summation. That's where in place of maximizing this likelihood function, we will maximize log likelihood. That is we have to. So if you do log, if you take log both sides, then what is it? Log is what? Log is inverse function of exponential. So if you apply log both sides, this exponential will be removed. It will be removed. Just we will have argument of this exponential function. So that means we are having this one in the log likelihood. In that's way it is easy to differentiate. So differentiate this one with respect to theta. After differentiation, what you are getting? You are getting this term, this argument twice. 2 and 1 by 2 will cancel out. So we are getting this term and equate to 0. After equating 0, what you will get? You will get one estimate of theta. That one is what? It is talking about average of the given data point of the data set. Average, it is talking about average of the given data. Okay, because here minus theta are coming 6 times. So 6 times theta equal to sum of 5 plus 6 plus 7 plus 8 plus 9 plus 10. So if you just simplify, then it is taking the form, this form, it is taking this form. So this is what this theta we are getting through what maximizing log likelihood, or I told that the same argument will be shared with likelihood function as well. So that's where this one is also optimal point for likelihood function as well. Likelihood. So this likelihood function we are getting an one estimator of mean, and if you try to visualize it, it is talking about average. So what is it is talking about average? That means it is coming with respect to sample. So this average we are calling it sample mean. So one estimator that for the, if your data is coming from normal distribution, then your estimator would be what? Nothing, just it is sample mean. Estimator of the maximum likelihood estimator of the mean would be just sample mean. And we know that what is meaning of sample mean? Sample mean is always unbiased estimator. So very nice. That means this is this estimation approach is a nice estimate. Directly we can say that it is directly giving sample mean. Now further, I would like to generalize. That one was just for 6 number of data. Now we can take any general kind of sample. Suppose we are having a sample of size n, that means n number of observation we observe. All these are coming from some normal distribution. I remember that this one is more complicated. Why? Here we don't know mean, also we don't know variance, so both are unknown to us. So your problem is more tedious, that we have to estimate both mean, mu and sigma square, both we have to estimate. So how we can define? First again, define the joint probability that will for this sample, joint probability for joint PDF for this sample, and that will give your what, likelihood function. And it is again dealing with product term. So what you do, take log likelihood. So take log likelihood. So here I have intentionally taken log likelihood. So what will happen? So there are various terms. So these are coming with respect to variance, and this one is dealing with uh, theta. That happens to be, we assume that it would give estimator of mean. Theta would give estimator of mean. So here I would like to put it here, estimator estimation. It is not here. Sigma would be also here. Sigma square would be here. So this sigma square cap, it is, we are talking about estimation, because here so sigma square is also known to us. So that's where we put estimation here. Okay, estimation. So how many terms? So this term is what? It is just having only one. This one is constant, log of ln 2 pi. It is a constant, and n is also constant, because it is talking, n is what, sample size. So n would be also constant. So we don't while optimizing this function log likelihood, we don't include this one. This one is meaningless. It is just a constant. So we have to focus over this one. When you try to estimate variance, then this one is important. When you try to estimate mean, this one is important. This one, when you try to estimate then variance, you need to differentiate with respect to this sample variance. So and I should not call it sample variance right now. It is one kind of estimator. Okay, sample variance I had already. That's why I am taking notation sigma sigma cap sample deviation it might be, but it may not be what unbiased estimator. It may be a bias estimator. So just I'm not taking s notation here. Intentionally I haven't taken s notation. I'm taking sigma cap notation, because s is meant for what, s is meant for unbiased sample deviation. Unbiased, or s square is corresponding sample variance. It is unbiased. That definition I had already taken. So here I'm taking sigma cap, because we don't know the biasness of sigma cap, this deviation we don't know right now. It may be biased, it may be unbiased. After getting explicit form of this one, then we can say that whether it will be biased or unbiased. So we will do to estimate this sigma. Okay, how we can estimate? So first we will estimate the mean. So in order to estimate mean, we need to differentiate this log likelihood function with respect to theta. If you differentiate after simplification, just do little bit simpler. It is a very nice function. It involves quality. So very nice function. Just keep on simplification. After that simplification, you will come to see that the estimate of theta, simplify it to what, x1 plus x2 up to xn divided by n. So what does it talk about? It is your sample mean. It is sample mean x bar, sample mean. So sample mean is what we had already discussed several times. Sample mean is an unbiased estimator of mean. So and hence this estimator, what you got with respect to this likelihood function or log likelihood function, that we are getting an unbiased estimator. Now we will try to find another thing, that estimator of variance. So one job is done. So this what estimator we got it through maximum likelihood approach. That one is a unbiased estimator, because it is a sample mean. So that's why it is unbiased estimator. Unbiased estimator. Now we will try to find one estimator of variance. So in order to get that, we need to differentiate with respect to sigma cap square. Okay, so if you differentiate and simplify it, you will come to see that maximum likelihood estimator of variance is what? It is coming like this way. A square of sum of a square of mean deviation. Here that sum is varying from that sample size 1 to n. Okay, divide by n. So n is coming here. So this estimator is not equal to sample variance. It is not equal to, why? I had already mentioned that sample variance include one bias Bessel correction, that 1 by n minus 1 factor, 1 by 1 by n minus 1 factor summation over xi sample mean will include it here. So this one is s square. So that's why, but here through this maximum likelihood approach, we are getting another kind of sample variance. So it is not equal to s square. So we can say that whatever estimator for variance we are getting with respect to this maximum likelihood approach, that one is not a unbiased estimator. It is a biased estimator. So this estimator is it is a biased estimator. So it is not a good estimation. But mean, for mean, what estimator we are getting? It is a unbiased estimator. Why? Because it was a sample mean. It was a sample mean x bar. So that's why for, so that's why maximum likelihood is estimation is good for mean and not good for what we call it variance. It is not good for variance. You will see that least square would be better estimation technique for variance. Later we will see that. So regarding, it is already above 2. So today we will wind up this class.